A 70-gram yo-yo has a diameter of 5.4 centimeters. The string winds around the axle with a diameter of 2 centimeters. Its rotational inertia or moment of inertia about an axis that goes through its center of mass is 3.83 times 10 to the negative fifth kilograms meter squared. With the top of the string fixed in place, the yo-yo is released from rest. Find the yo-yo's downward acceleration and the tension in the string. When the yo-yo accelerates downward, it rotates about its center of mass, while the center of mass goes downward. The yo-yo does not rotate about a fixed axis. It rolls without slipping along the string. So the yo-yo does both rotation and translational motion. It rotates about its center of mass, while the axis, the center of mass, does translational motion. In these problems we worked on in previous lessons, the boxes only do translational motion, while the cylinder and the pulley do rotational motion only. Now for the yo-yo, it does both translational motion and the rotational motion. We're looking for acceleration and tension, so we can draw a force diagram and write force or torque equation. Because the yo-yo is doing both translational and rotational motion, we have to write both net force equals to ma and the net torque equals to I alpha for the same object. So the acceleration goes down, and we have mg acting on the yo-yo. And where do we draw the mg? We draw it from the center of mass, so we have mg right here. The mass is 70 grams, that's 0.07 kilograms. So it's 0.07, I'm just going to round the g to 10, so this gives me 0.7 newtons. The yo-yo is touching the string. The string gives us tension. Tension is a contact force, so we should draw the tension at the contact point right here. And tension is a pulling force, so that's the tension. The yo-yo is not touching anything else, so that's it for our force diagram. Now let's write the net force equals to ma. The acceleration goes down, so the downward force is bigger. So it's the downward force minus the smaller one equals to m, which is 0.07 times the acceleration. And then we can write the net torque equals to I alpha. The torque is produced by the tension because mg goes through the axis, so mg does not provide any torque. So the tension provides torque, and the torque equals to the lever arm times the force. What is the lever arm? The lever arm is the distance between the line of force and the axis. So it is this distance. Since the diameter here is 2 centimeters, the lever arm here must be 1 centimeter, which is 0.01 meter. And this should equal to I 3.83 times 10 to the negative fifth times alpha. Because this part is rolling without slipping along the string. So the alpha and A, they are related. Alpha would be A over R. The string wraps around this portion with a radius 1 centimeter, so the R is 0.01 meter. Now we have two equations and two unknowns, so we can solve for our two unknowns any way we want. But if we want to stack these two so we can add them so that the minus t and the t can cancel, then we have to have t, 1t on this side, not 0.01 t. So what we can do is to divide both sides by 0.01. And then these two cancel, we have t on this side, and then on that side I would have 3.83 times 10 to the negative fifth divided by 0.01 and then divided by 0.01 again. And this will give me 0.383 times A. Now I can stack them and add them. The tension would cancel, so I get 0.7 equals to 0.07 plus 0.383. That gives me 0.453 times the acceleration. And this will give me acceleration equals to 1.55 meters per second squared. And I can plug this back in there, and I will have tension that is 0.592 newtons. Let me ask you one more question. You see, the center of mass of the yo-yo is at the center, while the supporting string is off-centered. After the yo-yo is released from rest, does it swing to the left a little as it goes down? Or does it just come straight down? Let's try it. It went straight down, didn't it? How about this spool? For this spool, the string is off-centered even more than the yo-yo. Do you think it is going to swing a little bit as it goes down? Let's see. Why do you think both of them went straight down without swinging to the left? Because the yo-yo starts from rest, and there are only vertical forces acting on the yo-yo. There is no horizontal force component on the yo-yo. Therefore, the yo-yo with no initial horizontal motion would continue to have no horizontal motion. So the yo-yo accelerates straight down.